Software Design Pattern from Wikipedia, the free encyclopedia. In software engineering, a software design pattern is a general, reusable solution to a commonly occurring problem within a given context in software design. It is not a finished design that can be transformed directly into source or machine code. It is a description or template for how to solve a problem that can be used in many different situations. Design patterns are formalized best practices that the programmer can use to solve common problems when designing an application or system. Object-oriented design patterns typically show relationships and interactions between classes or objects, without specifying the final application classes or objects that are involved. Patterns that imply mutable state may be unsuited for functional programming languages. Some patterns can be rendered unnecessary in languages that have built-in support for solving the problem they are trying to solve, and object-oriented patterns are not necessarily suitable for non-object-oriented languages. Design patterns may be viewed as a structured approach to computer programming intermediate between the levels of a programming paradigm and a concrete algorithm. Practice. Design patterns can speed up the development process by providing tested, proven development paradigms. Effective software design requires considering issues that may not become visible until later in the implementation. Freshly written code can often have hidden subtle issues that take time to be detected, issues that sometimes can cause major problems down the road. Reusing design patterns helps to prevent such subtle issues, and it also improves code readability for coders and architects who are familiar with the patterns. In order to achieve flexibility, design patterns usually introduce additional levels of indirection, which in some cases may complicate the resulting designs and hurt application performance. By definition, a pattern must be programmed anew into each application that uses it. Since some authors see this as a step backward from software reuse as provided by components, researchers have worked to turn patterns into components. Meyer and Arnaud were able to provide full or partial componentization of 2/3 of the patterns they attempted. Software design techniques are difficult to apply to a broader range of problems. Design patterns provide general solutions, documented in a format that does not require specifics tied to a particular problem. Structure. Design patterns are composed of several sections. Of particular interest are the structure, participants, and collaboration sections. These sections describe a design motif, a prototypical microarchitecture that developers copy and adapt to their particular designs to solve the recurrent problem. Described by the design pattern. A microarchitecture is a set of program constituents, example classes, methods, and their relationships. Developers use the design pattern by introducing in their designs this prototypical microarchitecture, which means that microarchitectures in their designs will have structure and organization similar to the chosen design motif. Domain-specific patterns. Efforts have also been made to codify design patterns in particular domains, including use of existing design patterns as well as domain-specific design patterns. Examples include user interface design patterns, information visualization, secure design, secure usability, web design, and business model design. The annual Pattern Languages of Programming Conference proceedings include many examples of domain-specific patterns. Design patterns were originally grouped into the categories, creational patterns, structural patterns, and behavioral patterns, and described using the concepts of delegation, aggregation, and consultation. For further background on object-oriented design, see coupling and cohesion, inheritance, interface, and polymorphism. Another classification has also introduced the notion of architectural design pattern that may be applied at the architecture level of the software, such as the model view controller pattern. Anti-pattern. From Wikipedia, the free encyclopedia. An anti-pattern is a common response to a recurring problem that is usually ineffective and risks being highly counterproductive. The term, coined in 1995 by Andrew Koenig, was inspired by a book, Design Patterns, which highlights a number of design patterns in software development that its authors considered to be highly reliable and effective. The term was popularized 3 years later by the book Anti-Patterns, which extended its use beyond the field of software design to refer informally to any commonly reinvented but bad solution to a problem. Examples include analysis paralysis, cargo cult programming, death march, groupthink and vendor lock-in. Definition. According to the authors of Design Patterns, there must be at least two key elements present to formally distinguish an actual anti-pattern from a simple bad habit, bad practice, or bad idea. A commonly used process, structure, or pattern of action that, despite initially appearing to be an appropriate and effective response to a problem, has more bad consequences than good ones. Another solution exists that is documented, repeatable, and proven to be effective. Examples: social and business operations. Organizational. Analysis paralysis, a project stalled in the analysis phase, unable to achieve support for any of the potential plans of approach. Bicycle shed, giving disproportionate weight to trivial issues. Bleeding edge, operating with cutting-edge technologies that are still untested or unstable, leading to cost overruns. Underperformance or delayed delivery. Bystander apathy, the phenomenon in which people are less likely to or do not offer help to a person in need when others are present. Cash cow, a profitable legacy product that often leads to complacency about new products. Design by committee, the result of having many contributors to a design, but no unifying vision. Escalation of commitment, failing to revoke a decision when it proves wrong. Groupthink, a collective state where group members begin to, often unknowingly, think alike and reject differing viewpoints. Management by objectives, SAFE, management by numbers, focus exclusively on quantitative management. Criteria, when these are non-essential or cost too much to acquire. Micromanagement, ineffectiveness from excessive observation, supervision, or other hands-on involvement from management. Moral hazard, insulating a decision-maker from the consequences of their decision. Mushroom management, keeping employees in the dark and fed manure, also left to stew and finally canned. Peter principle, continually promoting otherwise well-performing employees up to their level of incompetence, where they remain indefinitely. Seagull management, management in which managers only interact with employees when a problem arises, when they fly in, make a lot of noise, dump on everyone, do not solve the problem, then fly out. Stovepipe or silos, an organizational structure of isolated or semi-isolated teams, in which too many communications take place up and down the hierarchy, rather than directly with other teams across the organization. Typecasting, locking successful employees into overly safe, narrowly defined, predictable roles based on their past successes rather than their potential. Vendor lock-in, making a system excessively dependent on an externally supplied component. Project management. Cart before the horse, focusing too many resources on a stage of a project out of its sequence. Death march, a project whose staff, while expecting it to fail, are compelled to continue, often with much overwork. By management which is in denial. 90-90 rule, tendency to underestimate the amount of time to complete a project when it is nearly done. Over-engineering, spending resources making a project more robust and complex than is needed. Scope creep, uncontrolled changes or continuous growth in a project's scope, or adding new features to the project after the original requirements have been drafted and accepted, also known as requirement creep and feature creep. Smoke and mirrors, demonstrating unimplemented functions as if they were already implemented. Brooks's law, adding more resources to a project to increase velocity, when the project is already slowed down by coordination overhead. Software engineering. Software design. Abstraction inversion, not exposing implemented functionality required by callers of a function/method/constructor, so that the calling code awkwardly re-implements the same functionality in terms of those calls. Ambiguous viewpoint, presenting a model, usually object-oriented analysis and design, OOAD, without specifying its viewpoint. Big ball of mud, a system with no recognizable structure. Database as IPC, using a database as the message queue for routine inter-process communication where a much more lightweight mechanism would be suitable. Gold plating, continuing to work on a task or project well past the point at which extra effort is not adding value. Inner platform effect, a system so customizable as to become a poor replica of the software development platform. Input kludge, failing to specify and implement the handling of possibly invalid input. Interface bloat, making an interface so powerful that it is extremely difficult to implement. Magic push button, a form with no dynamic validation or input assistance, such as drop-downs. Race hazard, failing to see the consequences of events that can sometimes interfere with each other. Stovepipe system, a barely maintainable assemblage of ill-related components. Inside out, publishing the internal model to the outside world. Object-oriented programming. Anemic domain model, the use of the domain model without any business logic. The domain model's objects cannot guarantee their correctness at any moment, because their validation and mutation logic is placed somewhere outside, most likely in multiple places. Martin Fowler considers this to be an anti-pattern, but some disagree that it is always an anti-pattern. Call super, requiring subclasses to call a superclass's overridden method. Circle ellipse problem, subtyping variable types on the basis of value subtypes. Circular dependency, introducing unnecessary direct or indirect mutual dependencies between objects or software. Modules. Constant interface, using interfaces to define constants. God object, concentrating too many functions in a single part of the design, class. Object cesspool, reusing objects whose state does not conform to the, possibly implicit, contract for reuse. Object orgy, failing to properly encapsulate objects permitting unrestricted access to their internals. Poltergeists, objects whose sole purpose is to pass information to another object. Sequential coupling, a class that requires its methods to be called in a particular order. Yo-yo problem, a structure, example of inheritance, that is hard to understand due to excessive fragmentation. Programming. Accidental complexity, programming tasks which could be eliminated with better tools, as opposed to essential. Complexity inherent in the problem being solved. Action at a distance, unexpected interaction between widely separated parts of a system. Boat anchor, retaining a part of a system that no longer has any use. Busy waiting, consuming CPU while waiting for something to happen, usually by repeated checking instead of messaging. Caching failure, forgetting to clear a cache that holds a negative result, error, after the error condition has been corrected. Cargo cult programming, using patterns and methods without understanding why. Coding by exception, adding new code to handle each special case as it is recognized. Design pattern, the use of patterns has itself been called an anti-pattern, a sign that a system is not employing enough abstraction. Error hiding, catching an error message before it can be shown to the user and either showing nothing or showing a meaningless message. This anti-pattern is also named diaper pattern. Also can refer to erasing the stack trace. During exception handling, which can hamper debugging. Hardcode, embedding assumptions about the environment of a system in its implementation. Lasagna code, programs whose structure consists of too many layers of inheritance. Lava flow, retaining undesirable, redundant or low quality code because removing it is too expensive or has unpredictable consequences. Loop switch sequence, encoding a set of sequential steps using a switch within a loop statement. Magic numbers, including unexplained numbers in algorithms. Magic strings, implementing presumably unlikely input scenarios, such as comparisons with very specific strings, to mask functionality. Repeating yourself, writing code which contains repetitive patterns and substrings over again, avoid with once and only once, abstraction principle. Shooting the messenger, throwing exceptions from the scope of a plugin or subscriber in response to legitimate input, especially when this causes the outer scope to fail. Shotgun surgery, developer adds features to an application codebase which span a multiplicity of implementers or implementations in a single change. Soft code, storing business logic in configuration files rather than source code. Spaghetti code, programs whose structure is barely comprehensible, especially because of misuse of code. Structures methodological. Copy and paste programming, copying, and modifying existing code rather than creating generic solutions. Every fool their own tool, failing to use proper software development principles when creating tools to facilitate the software development process itself. Original research. Golden hammer, assuming that a favorite solution is universally applicable, see silver bullet. Improbability factor, assuming that it is improbable that a known error will occur. Invented here, the tendency towards dismissing any innovation or less than trivial solution originating from inside the organization, usually because of lack of confidence in the staff. Not invented here, NIH, syndrome, the tendency towards reinventing the wheel, failing to adopt an existing adequate solution. Premature optimization, coding early on for perceived efficiency, sacrificing good design, maintainability, and sometimes even real-world efficiency. Programming by permutation, or programming by accident, or programming by coincidence trying to approach a solution by successively modifying the code to see if it works. Reinventing the square wheel, failing to adopt an existing solution and instead adopting a custom solution which performs much worse than the existing one. Silver bullet, assuming that a favorite technical solution can solve a larger process or problem. Tester-driven development, software projects in which new requirements are specified in bug reports. Configuration management. Dependency hell, problems with versions of required products. DLL hell, inadequate management of dynamic link libraries, DLLs, specifically on Microsoft Windows. Extension conflict, problems with different extensions to classic Mac OS attempting to patch the same parts of the operating system. Jar hell, overutilization of multiple jar files, usually causing versioning and location problems because of misunderstanding of the Java class loading model. Creational pattern. In software engineering, creational design patterns are design patterns that deal with object creation mechanisms. Trying to create objects in a manner suitable to the situation. The basic form of object creation could result in design problems or in added complexity to the design. Creational design patterns solve this problem by somehow controlling this object creation. Creational design patterns are composed of two dominant ideas. One is encapsulating knowledge about which concrete classes the system uses. Another is hiding how instances of these concrete classes are created and combined. Creational design patterns are further categorized into object creational patterns and class creational patterns. Where object creational patterns deal with object creation and class creational patterns deal with class instantiation. In greater details, object creational patterns defer part of its object creation to another object, while class creational patterns defer its object creation to subclasses. 5 well-known design patterns that are parts of creational patterns are the Abstract Factory Pattern, which provides an interface for creating related or dependent objects without specifying the object's concrete classes. Builder Pattern, which separates the construction of a complex object from its representation so that the same construction process can create different representations. Factory Method Pattern, which allows a class to defer instantiation to subclasses. Prototype Pattern, which specifies the kind of object to create using a prototypical instance, and creates new objects by cloning this prototype. Singleton pattern, which ensures that a class only has one instance, and provides a global point of access to it. Definition. The creational patterns aim to separate a system from how its objects are created, composed, and represented. They increase the system's flexibility in terms of the what, who, how, and when of object creation. Usage. As modern software engineering depends more on object composition than class inheritance, emphasis shifts away from hard-coding behaviors toward defining a smaller set of basic behaviors that can be composed into more complex ones. Hard-coding behaviors are inflexible because they require overriding or re-implementing the whole thing in order to change parts of the design. Additionally, hard-coding does not promote reuse and makes it difficult to keep track of errors. For these reasons, creational patterns are more useful than hard-coding behaviors. Creational patterns make design become more flexible. They provide different ways to remove explicit references in the concrete classes from the code that needs to instantiate them. In other words, they create independency for objects and classes. Consider applying creational patterns when a system should be independent of how its objects and products are created. A set of related objects is designed to be used together. Hiding the implementations of a class library or product, revealing only their interfaces. Constructing different representation of independent complex objects. A class wants its subclass to implement the object it creates. The class instantiations are specified at runtime. There must be a single instance and client can access this instance at all times. Instance should be extensible without being modified. Structure. Creational pattern class diagram. Below is a simple class diagram that most creational patterns have in common. Note that different creational patterns require additional and different participated classes. Participants. Creator, declares object interface. Returns object. Concrete creator, implements objects interface. Some examples of creational design patterns include Abstract factory pattern, a class requests the objects it requires from a factory object instead of creating the objects directly. Factory method pattern, centralize creation of an object of a specific type choosing one of several implementations. Builder pattern, separate the construction of a complex object from its representation so that the same construction process can create different representations. Dependency injection pattern, a class accepts the objects it requires from an injector instead of creating the objects directly. Lazy initialization pattern, tactic of delaying the creation of an object, the calculation of a value, or some other expensive process until the first time it is needed. Object pool pattern, avoid expensive acquisition and release of resources by recycling objects that are no longer in use. Prototype pattern, used when the type of objects to create is determined by a prototypical instance, which is cloned to produce new objects. Singleton pattern, restrict instantiation of a class to one object. Structural pattern. From Wikipedia, the free encyclopedia. Jump to navigation, jump to search. In software engineering, structural design patterns are design patterns that ease the design by identifying a simple way to realize relationships among entities. Examples of structural patterns include adapter pattern, adapts one interface for a class into one that a client expects. Adapter pipeline, use multiple adapters for debugging purposes. Retrofit interface pattern, an adapter used as a new interface for multiple classes at the same time. Aggregate pattern, a version of the composite pattern with methods for aggregation of children. Bridge pattern, decouple an abstraction from its implementation so that the two can vary independently. Tombstone, an intermediate lookup object contains the real location of an object. Composite pattern, a tree structure of objects where every object has the same interface. Decorator pattern, add additional functionality to a class at runtime where subclassing would result in an exponential rise of new classes. Extensibility pattern, aka framework, hide complex code behind a simple interface. Facade pattern, create a simplified interface of an existing interface to ease usage for common tasks. Flyweight pattern, a large quantity of objects share a common properties object to save space. Marker pattern, an empty interface to associate metadata with a class. Pipes and filters, a chain of processes where the output of each process is the input of the next. Opaque pointer, a pointer to an undeclared or private type, to hide implementation details. Proxy pattern, a class functioning as an interface to another thing. Behavioral pattern. From Wikipedia, the free encyclopedia. In software engineering, behavioral design patterns are design patterns that identify common communication patterns among objects and realize these patterns. By doing so, these patterns increase flexibility in carrying out this communication. Examples of this type of design pattern include: Blackboard design pattern provides a computational framework for the design and implementation of systems that integrate large and diverse specialized modules, and implement complex, non-deterministic control strategies. Chain of responsibility pattern, command objects are handled or passed on to other objects by logic containing processing objects. Command pattern, command objects encapsulate an action and its parameters. Externalize the stack, turn a recursive function into an iterative one that uses a stack. Interpreter pattern, implement a specialized computer language to rapidly solve a specific set of problems. Iterator pattern, iterators are used to access the elements of an aggregate object sequentially without exposing its underlying representation. Mediator pattern, provides a unified interface to a set of interfaces in a subsystem. Memento pattern, provides the ability to restore an object to its previous state, rollback. Null object pattern, designed to act as a default value of an object. Observer pattern, aka publish/subscribe or event listener. Objects register to observe an event that may be raised by another object. Weak reference pattern, decouple an observer from an observable. Protocol stack, communications are handled by multiple layers, which form an encapsulation hierarchy. Scheduled task pattern, a task is scheduled to be performed at a particular interval or clock time, used in real time. Computing. Single serving visitor pattern, optimize the implementation of a visitor that is allocated, used only once, and then deleted. Specification pattern, recombinable business logic in a Boolean fashion. State pattern, a clean way for an object to partially change its type at runtime. Strategy pattern, algorithms can be selected on the fly, using composition. Template method pattern, describes the program skeleton of a program, algorithms can be selected on the fly, using inheritance. Visitor pattern, a way to separate an algorithm from an object.